I'm from the University of Kaiserslautern. This is pretty sure one of the last talks from this university because it's going to be renamed end of this year. So please enjoy. And yeah, I'm also talking about a little bit the gap between technical and biological systems. So on the technical system, if we look at today's robots, we have robots with a few actuators, mostly one actuator per joint. And in nature, we have a lot of muscles. And in technical system, we have, especially for walking with flat feet and very often bended knees because of the ZMP approach. But on nature, we are rolling over the heel, we are rolling over the toes, and we have, or we do not have a stable system. So we cannot stop, and we also cannot dynamically stop. We would just fall over. But this is more like falling from one step to the next. And also in the technical system, we have very high speed controllers to be able to calculate all these forces and precisely generate them. However, in nature, our nervous system is really slow compared to a technical system. But somehow it is working very well. So the question is how? And what are we doing wrong in our technical systems? And yeah, here are some issues. For example, the workspace. So in nature, we have a lot of degree of freedom, and every degree of freedom has a small range of motion. And now the question is this beneficial or is this not beneficial? So we cannot have circular motions by construction in nature. So this, is maybe not a beneficial feature, but maybe it is, because it is constructive, not possible to do it different. But if we check for actuators in series, then they sum up in velocity. So we have a lot of muscles in parallel summing up force, and we have a lot of actuators on all these small degree of freedom in series, which is summing up velocity. So maybe this is a feature. And this is something which is a little bit unknown at the moment. The next thing is actuator redundancy. So in nature, we have a lot of muscles, 2, 3, 4 muscles, which are located very similarly. And the question is it just not possible to make bigger muscles? Is it more energy efficient to have all these small muscles? Is it because of whatever, or is it just some outcome of evolution? The only thing which we know is that it's definitely robust against damage. If one muscle is broken, another one is just replacing it. This is for sure. Everything else is, I would say, still a little bit ongoing research. And why do we have muscles that span more than one joint? Especially, we just heard it at the ankle, we have 2 muscles, very similar at the Achilles tendon, one spanning one joint, one spanning 2 joints, but we have both of these. But we do not have the antagonistic one. So there should probably be a reason for this. And yeah, I was looking at the properties of a natural muscle. And there are some main properties among a lot of other ones. And these are somehow the relations between force and length, force and velocity, and also force and time of the muscle. So force and time, this is, well, that the muscle is getting tired. So probably this is nothing we want to have in a technical system. It's probably a drawback. Also, it might be some kind of self-protection mechanism. So we have a force-length relation and a force-velocity relation, which is left. And if we have a look at these curves on the bottom, we see the force-velocity relation on the right and the force-length relation on the left. And I think I have both on separate slides. No, I do not. So if we take the derivative of these curves, we have the stiffness and the damping characteristic of a muscle. And it's already seen, for example, on the left side that the stiffness has some positive and some negative part with shorten and longer, while the damping is only in the positive range. And from a control point of view, having a negative stiffness is not very good. So maybe we should focus on this damping characteristic of a muscle. And this is a little bit explained here. So we have for a control of a pair of antagonistic muscles, two characteristics here that seems to be quite useful, which is the force and the damping. Because the force of two antagonistic muscles can be subtracted from each other, while the damping is added. And now we have this feature that we can co-contract and change properties. And with this co-contraction, we can change the damping and the force. And we have two output parameters with two input parameters. And hopefully these two values make sense to be used for a better control. And if we think a little bit further, we also see that this damping is quite interesting characteristics because it keeps the system stable. And since this is a part of our intrinsic muscle properties, this damping is a zero delay feedback, kind of zero delay. So we are kind of overcoming the delay of our nervous system by pre-programming the damping of our limbs into the muscles. And now we need the variety of the muscles, because if we only would have one muscle for one joint, this would be very limited. But with this variety of muscles, we can really, let's say, program in the Cartesian workspace of the TCP, hand or foot or whatever, some kind of Cartesian damping. And this is what I have tried to implement in our robot. Unfortunately, there is no artificial muscle existing at the moment. So we were going for an electric actuator with some spring at one side to have this serious elastic element. and a motor on the right side, which is representing the contractile element. And as input, there is nothing but the force and the damping to this actuation unit, which is then representing a pair of antagonistic muscles. The good thing is that this is a very simple principle, so there is not too much filtering necessary, not too much computation necessary, and it is also very fast in reaction, especially for the damping, because obviously this is not a built-in property here. In order to get this to a whole body, we have to overcome a little bit of a mechanical problem. So here we have to solve some inverse kinematics problem to come from the workspace to the joint space. Then we have to somehow calculate this damping distributions of the muscles, and then, since we have more muscles than needed, we have to somehow distribute the force, because this force is still something which is redundant. And this is our planar biped robot called Carl. It is built in a way to mimic a human leg. So from the proportions and also from the actuation system, it has 5 muscles. So 2 biarticular muscles on the leg are in parallel to 3 monoarticular ones. And now I executed some circular compliant trajectories on this robot using this force and damping control approach. And this is the result. I just see it's the same picture. Okay, it should not be the same picture. Let's refer to, it's a picture from the right. So the black circle is the desired trajectory. It is executed at 120 rounds per minute. And I have different stiffnesses given to the system, which are these dotted ellipses. And depending on which stiffness I gave to the system executed different trajectories. And it can be seen that these stiffnesses, for example, the purple one means it is a kind of a horizontal ellipse. So not horizontal, vertical ellipse. So the vertical precision of the motion is increased compared to the red one, which is a very soft trajectory. And the orange one, you can see this is a very hard trajectory, very precise. And this is actually hitting the boundaries of the joints, but still it is robust. Time is over. I'm also done. So as a conclusion, I think there's no conclusion. So as you can see that in principle, the system is working. So if I increase the stiffness in Z or Y direction, the precision in Z or Y direction is increased. And this is a kind of, or can be interpreted as a co-contraction of the muscles, which can be also observed on humans or animals.